Okay. So levels lists all elements of a tree according to their levels. Another important way to render a tree as a list is what is called in-order listing. And what this does is recursively list all elements of the left subtree, then list the root after that, and then recursively list all elements of the right subtree. Okay. And the program couldn't be simpler. It's just transcribing that as a, in Haskell, in order listing of nil is just empty list. In order listing of node TL XTR is in order listing of TL plus singleton X plus in order listing of TR, right. So I can go back and do the in order listing of that earlier example that we had. Let me switch to VS Code now. Right, for the same tree, if I did in order of create tree access, yeah, you will see what is happening. You go first to the left subtree, you go to its left, you go to its left, you go to its left, 68. Then you list minus 120, then you go to the right, there is nothing. So you backtrack and go here. You are done with this whole left subtree of 78. So then you go back and you list 78, right. So you have 68 minus 120, 78. To the right of 78, you have this tree, its left subtree is 58. Then you list minus 35, then there is nothing on the right. So you go all the way back here, minus 130. Go to the right, go to the left here, go to the left here, minus 107, then print this, minus 172. There is nothing here, so you go up, minus 148, then you go to the right, 90. Then you go all the way back to here, minus 185, right. And then go to the right subtree now and continue like this. So this is another way of traversing. What is the importance of these different ways of creating a list from a tree? We will see this later, okay. Especially in order is important. Okay, let me go back to the slides now. So we have seen the code for in order. This is the code and we have seen how it works. Let's try to figure out how efficient in order is. So let Tn denote the number of steps needed to list a tree of size n. Then Tn is nothing but let NL and NR be the sizes of the left and right subtrees. Then Tn is you have to list the left subtree, you have to list the right subtree, but importantly you have to you do this plus, right. So you do in order of TR, this takes T of NR time, then you have to do a plus X, this will only take constant time. Or you can even think of it as X colon, you do not even need to do this, you can just say X colon one time, one step. But then you have to do plus of in order TL, right, this whole thing. So that will take, remember that plus takes time proportional to first argument. So here it will take time proportional to the length of TL, which is NL, okay. So that is why you have T of N is T of NL plus T of NR plus NL. Yeah, so now we do not know what the sizes of NL and NR are. It could be a left skew tree when the size of NL is n minus 1. It could be a right skew tree when the size of NL is 0, right. So we do not know really. The worst case is a left skew tree because NL is n minus 1 and NR is 0, and the same is true recursively of the left subtree as well. So your T of 0 is 0 and T of N is T of n minus 1 plus n minus 1, and if you unroll this recurrence, you will have n into n minus 1 by 2. So your this thing is in order for left skewed tree takes order n square time, where n is the number of nodes. Okay. So as usual the culprit is plus. So can we avoid doing plus? Okay, let us see how. Suppose you define go some local auxiliary function, go of TL to be in order T plus plus L. Okay, this is once again the thing about this thing. So this we will have to show that this whole thing does not depend on L. Complexity does not depend on L. Right, that is the whole idea here. Suppose you define go of TL to be in order T plus plus L, then what can you say? Suppose you can define go independently without using, independently means without using in order. Then you can now define in order in terms of go. In order of T is nothing but go of T empty list, because because go of T L is supposed to mean in order of T plus plus L, remember. So go T empty list will be in order T plus plus empty list, which will just be the in order T. Okay. So if you can define go without referring to in order, then you can define in order in terms of go. Okay, and that is what we want to do. And we will actually calculate the definition of go rather than trying any intuition or whatever. So go nil L is in order nil plus plus L, right, just according to definition. But in order nil is empty list. We already, so let's write this somewhere else. Just to recall, the previous definition of in order nil we had was this. In order nil is empty in order node TL x TR was in order TL plus plus singleton x plus plus in order TR. Okay, that is what we had. Okay, so in order nil is empty list, so this is empty list plus plus L, so that is L. Okay, so now you have go, you can define go nil of L to be L. Okay, and this does not refer to in order at all anywhere. Okay, you can just take the leftmost and rightmost steps and take that as the definition of go nil L. Go of node TL x TR L is what, let us expand this, it is in order of node TL x TR plus plus L, but in order of node TL x TR is what I have written here, in order TL plus plus x plus plus singleton x plus plus in order TR plus plus L. Oh, but plus plus is associative. So this is nothing but in order TL plus plus, and you shift the parenthesis here, singleton x plus plus in order TR plus plus L. But in order TR plus plus L is nothing but go of TRL by our definition, because go of TL is in order T plus plus L. So in order TR plus plus L is go TRL, and you are doing singleton list x plus plus, but that is nothing but saying x colon go TRL. Okay, now I have in order TL plus plus x colon go TRL, but once again in order TL plus plus anything is go of TL plus plus that. So now I can have this whole thing as go TL. I first do go TRL, then I put x before that, and then I do go TL that list. Okay, and that is my recurrence relation. Now the main point here is that you are avoiding the plus plus. Okay, that is what you are doing. Let's, in the next slide I will actually derive the time complexity for the new definition of go. Okay, so so you define now in order to be go T empty list, where go nil of L is L, go node TL x TR is go TL x colon go TRL. Okay, this is what you are doing. Now what is the time complexity of this? Once again, let Tn be the number of steps required to compute go TL, where T is the size of n, and the main point is that you do not care about L, because the length of L does not matter in this whole thing. Let NL and LR be the NR be the sizes of TL and TR. So then you have N itself is equal to NL plus NR plus 1. Tn is TNL, because you have to do go TL for some list, the size of that list does not matter. You have to do go TR for L, right. So this call of go will take TNR times, this call of go will take time TNL. So you have TNL plus TNR plus 1. 1 is the cost of adding colon, and that's basically it. So you keep expanding it. Finally, you will actually see that if you expand this recurrence, you will actually show that you can guess that the solution is n, and then you can actually verify that the solution is also n, because n is NL plus NR plus 1, and here T of n is, or if you want to take the cost of colon to be 5, let us say, so then you will add 5, but this is a linear thing, so it will be Tn equals 5n, because this is a linear function. You are saying T of NL plus NR plus 1 is T of NL plus T of NR plus 5, and now this really means if you keep on expanding that your original size of the tree is n, and your amount of time you take is 5n. Okay, so this is linear actually. It's a much better, so much better compared to order n squared. Okay, so we have seen some, we have seen in order. Now the next task, so if you have a tree, we know how to create a list in various ways. We want the reverse thing. You want to create a binary tree from a list. Okay, and this is a nice program. And while we are at it, right now there are no other constraints, but I will put one constraint. If I have a list, let's say 1, 2, 3, I could have formed a tree with root 1, right subtree 2, or to give you an even more dramatic example. So if I have 1, 2, 3 dot 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 10, from here I can go to 1, 2, so left subtree is empty. This is a right skewed tree. Right, this is really nothing but your original list, except that you are adding some nil 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 on the left. So this tree is not really a tree structure, it is almost like a list, right? It's like a comb if you think of it. Okay, comb. That is not what I want. What I want is that you create a binary tree from a list, but the tree should be as small height as possible, should have as small a height as possible. Let's try to see how to do that. As balanced as possible, not just as small a height, it should be as balanced as possible, and you will see that it's really perfectly balanced the way we do it. The strategy is split, you have a list, split the list into two halves, create a tree with the left half, create a tree with the right half, put a root on the top. Okay, so recursively create a binary tree from each half and join them together. How do you join them? By putting a root on top. Which would be the root? Let us see the details now. Right, so create tree is as follows. Create tree of empty list is null, because there is nothing to make a tree with. So create tree of excess, which is some arbitrary list, is node TLYTR, right? This is what I told. Create a left subtree, create a right subtree, join them together with a root. Now what do you take to be the root, etc., etc.? Let us check. M is length of excess div 2. Okay, note importantly, if length of excess is even, M is also even, but more importantly, so let n equals length of excess. M is exactly n by 2. If n odd, M is n minus 1 by 2. Right, because that is how div works. Okay, div 2, that is how it works. Now note that n is even, n cannot be 0, because we have handled that case already. Create tree of empty list is nil, right, and n is 0 means the list is empty. So now the list is non-empty. So now if the if the list is some even number, then you are splitting it here. Definitely, so if n is even and greater than 0 means that if you split at m x's and that is equal to y's comma z's, let us say, then definitely z's is non-empty. Why? Because m elements are on the left and m elements are on the right, and m is n div 2, right? So that is non-empty. Whereas if n is odd, in the very worst case, n could be 1. If n is 1, m is 0, but even then, split at 0 x's equals y z's, where z is non-empty. Right. So what is the point? The point is that no matter what, if you take m to be length of x's div 2, and if you do split at m x's, or in other words, take m x's. This is. Right. So if you right. So if you do split at mx's, or in other words, take mx's and drop mx's, the drop mx's will always be non-empty. So which is why I can say that TL is create tree of take mx's and y colon y's is drop mx's, right? I am able to actually say pattern match drop mx's against y colon y's, because there will always be an element there. And TR is create tree of y's, okay? And then these three things are what I am putting together, okay? Node TL YTR, where TL is create tree of take mx's, y colon y's is drop mx's, but the y I will promote to the root, and TR is create of y's, create tree of y's, okay? So now, yes, this is a good exercise. So if I create the tree of 0 colon 14, if I try to do the DF, the breadth first listing, it should give me this, because the root will be 7, the left root will be 3, it's perfectly balanced, you see. So if I start with 0 to 14, there are 15 elements here, and m, which is n div 2, will be 7, right, because 15 div 2, and that would mean that your left tree is formed using elements from 0 to 6, and the right tree is formed using elements from 8 to 14, and 7 is the root. So you will put 7 here, and then you will try to create a tree with this. Once again, 0 to 6 has 7 elements, so 7 div 2 is 3. So you will take the first 3 elements and create a tree. You will take the remaining list, but that will have one element which you will promote to the root. So 3 will become the root, and you can see that I will create a tree like this. Okay, that is the tree I would create. It's perfectly balanced. There are 15 elements, but the height is 1, 2, 3, 4. Okay, good. So we have done this, but once again there is a problem, because let's now try to see how efficient this program is. Okay. So clearly length take and drop take linear time. So at every point of time in the recursive call, as you would have noticed, I would have to do this length x's div 2. So I have to calculate length, I have to do take m, I have to do drop m. So these things take linear time for the list. Okay. So take time proportional to some c n, where c is a fixed constant. n is the length of the list. Okay, I'm what I mean is that together time taken by length take drop together equals some c times n. Okay, good. So if I write a recurrence, so T of n is, I have to create a tree with the left half of the list and I have to create a tree with the right half of the list, that is n by 2. So I have to do it twice, so 2 times n by 2 plus order of n, let us call it Cn. Okay, but this is a recurrence that we have already written for merge sort etc. It is actually T of n is order n log n time. Okay. So we have a method for creating a binary tree from a list which works in time order n log n. Can we do better once again, right? The point is we are doing this length, take, drop, etc. all every time during every recursive call. Can we somehow avoid doing length every time, take every time and drop every time? So the culprit is repeated use of length, take and drop. The problem remains even if we use splitet, because take separately and drop separately will take for m will take m plus m time, but splitet will take m time. In any case, you will have to pay the same price. So can you avoid that? Okay. So you can actually derive a more efficient create tree by avoiding length in the recursive calls. Here is the new, you could actually derive it, but I am directly presenting the program and the intuition should be clear. So I am calling this CT instead of Go. Create tree of x's is CT of length x's x's. So what is the idea here? The idea here is that CT is of type int arrow list int a arrow list a int arrow list a arrow just a B tree of a. What does it do? CT of n x's Yeah, so we'll create a B tree out of the first n elements of x's. Right, if I do that, then I can avoid repeated calculation of length in the recursive calls, because you notice here CT of length x's x's and now CT of 0 x's is nil, because to create a tree out of 0 elements means the tree is nil. CT of n x's is node TL by TR. It is the same program as earlier, except m is n div 2, rather than calculating length we are directly doing this. And when you make a recursive call, you will say, oh, CT TL is CT m take m x's, y call inverse is drop m x's. Okay, so it is the same m, except that instead of recursively computing length every time, you are just computing length once and then taking it as an extra parameter, and whenever you make the recursive calls, you are taking this m and m, those are n div 2, that is an extra parameter. Okay, and finally TR is CT of n minus m minus 1 y's, because if you want to create a tree out of n elements, there are some other elements left over, then what I am doing is I am first trying to create a tree out of m elements, then there is one root, and then how many elements are left over here? N minus m minus 1. Okay, so I need to make a tree out of n minus m minus 1 elements of y's, and that will be my right subtree. Okay, so this I can do, but still there is a problem because I still do take and drop. So I need to avoid take and drop as well. And here is where let go of n x's be CTN of take n x's comma drop n x's. If I do that, I can do the same derivation as earlier. then create tree of x's is first of go length xs xs. Okay, instead of ct I am just using go, but go will not only produce the tree, it will produce the remainder of the list. Okay, so that is the real point. Go n x's, create a tree, it will return a pair, One part of the pair is other part of the pair is drop n x's. All the remaining elements. Okay, so that is what this go will do. Okay, now I can directly program go, because go n x's is now I am actually calculating the definition of go. Go n x's ct n of take n x's drop n x's, that is equal to node tl by tr comma drop n x's, where m is endiv to tl comma void colon rest is ctm of take m of take n x's, right, because that is what this does, ctm of take m x's comma drop m x's. So that is what I am doing, ctm of take n x's, but take m of take n of x's is nothing but take m of x's. Why? Because m is smaller than n, and if you have a list, if you first take the first n elements and then take the first m elements out of this, that is the same as taking m elements out of. Right, it does not matter whether you are taking from take n x's or from x's itself. If you are taking m elements, that is the same. Okay, fine. And what is drop m of take n x's? So this is also something that you have to see. If I take n elements and if I drop m elements, that is because I am dropping these elements. Okay, so we need to do some calculation. So take n, drop m of take n of x's is nothing but yeah. So if I take n elements and then drop m elements, that is the same thing as first dropping m elements and then I have to take the remaining elements. The remaining elements are n minus m. Okay, so drop m of take n of x's is the same as take n minus m of drop m of x's. Okay, okay. So here is the calculation. So take m of take n of x's is take m of x's. Y colon rest is drop m of take n of x's, that is the same as take n minus m of drop m of x's, that is the same as take n minus m of y colon y's, but that is also the same as y colon take n minus m minus 1 of y's. So rest is actually take of n minus m minus 1 of y's. Drop n x's is drop n minus m of drop m of x's, that is, yeah, because if you have to drop n elements, you can achieve the same thing by first dropping n minus m elements and then dropping m elements, or in other words, in this case, first dropping m elements and then dropping n minus m elements out of those. But drop m x's is y colon y's, as we have said here. So this is nothing but drop of n minus m of y colon y's, but I have y followed by y's and I have to drop n minus m elements in this. That is the same as dropping n minus m minus 1 elements of y's. Okay, so now what have I done? I have done, if I have expressed everything in terms of take and drop of n minus m minus 1, okay, on y's. So let us see if this helps. So once again, go of n x's is node tl by tr comma drop n minus m minus 1 y's, where m is endiv to tl y colon y's is ct of m of I have done all the substitutions here. Okay, CT of m of take m excess, drop m excess. TR is CT of n minus m minus 1 of take n minus m minus 1 y is the same as this. Okay, I have this. I urge you to go back and check these calculations. I have done all the calculations and you finally have this. Okay, so now I remember that I started out by saying that go of n excess was defined to be this, right? CT of n of take n excess, drop n excess. That is the point. Yeah. Go some generic K, let us say. Okay, so this portion here is nothing but go m excess. No, this whole portion here is go m excess. Okay, and this and this portion is CT n minus m minus 1 take n minus m minus 1 y's, and here you have drop n minus m minus 1 y's. So if you put these two things together, okay, so let's see how the program works. No, so your go n excess is nothing but node TLYTR comma Z's, where m is n div 2, TL comma y colon y's is go m excess, TR comma Z's is go n minus m minus 1 y's. Now I have derived this, but it is also intuitive. Okay, so let me give an intuitive explanation. Yeah, so what you want to do is go K excess in general will create a B tree out of first K elements comma rest of x's. Okay, so now how do I do this recursively? I go here, I go n x's, so go 0 x's is nil comma x's, because I have to give the rest of x's. I have consumed only 0 elements, so this is the whole of x's. Go n x's is node TLYTR comma z's, where z's is whatever you get after dropping n elements. But how do you derive that? You derive that by saying, oh, I will, so I have this, these are the first n elements. So this itself I will do by first taking m elements, creating a tree out of that and giving the remainder of the list, and that list would be y colon y's. Now make y the root, and I have this whole list. In that whole list I will have to pick n minus m minus 1 elements and do this same procedure. So create a tree out of n minus m minus 1 elements and give the return, give the remainder of the list. Okay, so this is essentially a very smart create tree. It is also intuitive, even though I tried to go through a rigorous derivation of this program. Okay, so what is the time complexity now? Time complexity is 2t n by 2 plus c, because I have to do go of n, I have to do go n minus m minus 1 and go m. These are both approximately n by 2. So I have two recursive calls, and that is it. There is no other length or plus or take or drop or anything. There is one length computation at the very beginning, but that is not part of go, that is part of create tree. Okay, so if I have this, then I will have Tn is 2n minus 1 times c or whatever, and that is order n. I have an order n procedure to create a balanced tree out of a list. Okay, so that is the takeaway here. And I need to be able to show a binary tree easily, and this is one thing that I actually have a much more sophisticated show. You can refer to the code and figure it out, but I want to do something like this, and this is not a very complicated program. I can actually yeah, so what you want to do is that okay, so at every level I have an indentation. Okay, so the original tree will be printed at 0 indentation. Every subsequent its subtree will be printed at 0 plus 2 indentation. Its subtrees will be printed at indentation 4, etc., etc. So this is all I am doing. So and also what I am doing is I am creating yeah. So what I am creating is a list of strings, as I see here. One string corresponds to whatever I want to print on each line, and if I concatenate all them, I will get one whole string, which if I do, it will print line by line by line. Okay, so n is the indentation level. Go n nil. I don't have to instead of the nil tree, I will put a star here. So I will indent n levels and I will print a left bracket and star and right bracket. Go n node nil x nil will be, I will indent n levels and I will just show x, because x doesn't have any subtrees. But the general case is go n node tl xtr. Now what I will do is I will indent n levels and I will print I will first print the root by putting the left parenthesis and showing this, and I will create a new line, and below with indentation n by 2 I will print the left subtree, and then there will be one line which will I will add one line to do a new line, and then I will print the right subtree at indentation level n plus 2, and then I will add another new line, and finally I will print the corresponding right square bracket that corresponds to this. These two are matching, okay, at the same indentation level. Okay, and what is indentation? Indentation just means I will replicate space n times and then put whatever string I want to put. That is how I indent a string. This is my code, and in fact we have even more sophisticated code for show, and this is all I have to say about binary trees. When in the next lecture we will actually make proper use of binary trees by adding some more structure to it and creating what are called binary search trees. That is for the next lecture. Thank you.